This is a video about atomic structure. I think you guys probably know a lot of this from having science in 9th grade. But we are talking about the protons and neutrons and electrons and the mass number, the atomic mass unit, and different isotopes and ways to write the isotope notation. So the atom is the smallest particle that is still going to act like that particular element. So like an atom of carbon is going to act like carbon. If you go smaller than that, you would get into the subatomic particles, protons, electrons, neutrons, and even further like quarks. Those are not unique to each element. So the atom is the smallest that you can get to. Can we actually see atoms? Kind of. So we can use a scanning tunneling electron microscope and trace, it's very complicated, but trace, essentially it's like tracing the outside of the electron cloud. This is an actual image of silicon atoms. This is a video that shows how they can manipulate the atoms. So I will make that bigger for you.
We can look up at the sky and see the stars and nebulas.
So each of the spheres in the movie are atoms, and they were manipulating the movement of the atoms to make this video. So I will include a link if you guys want to learn more on how they actually did that. So if we start talking about the atom, the first, I think, most important part is the atomic number. The atomic number is the number of protons, and that's the only number that really determines what element it is. So if it's mercury, it's going to have an atomic number of 80. If it doesn't have an atomic number of 80, it's not mercury. So the neutrons and electrons, the mass number can all change, but 80 means mercury, 6 means carbon. So the atomic number identifies the element, and it's the number of protons. A proton is equal in mass to something we call an atomic mass unit, or AMU. So one proton and one neutron are about 1 AMU. If you go out a bunch of decimal places, they're a little bit different, but essentially their mass is equal to one of these mass units. And the mass unit is something that we made up. We didn't want to use grams. Even micrograms and nanograms would have been too big. So what we do is we take a carbon atom, and 1/12 of the carbon atom is kind of like a piece of the pie. That's what an AMU is. So everything is massed in relative to a carbon atom. Isotopes, remember I said that the atomic number cannot change, or otherwise it's a new element, but isotopes are the same element, but they just have a different mass. And the reason they have a different mass is because they have a different number of neutrons. So the neutron number can change. When you're younger, or in 9th grade or even before, A lot of times people assume protons and neutrons are equal, and they can be, but they're not always equal. In fact, as elements get bigger, more and more neutrons are needed to hold the nucleus together. And there are different types. Almost everything has several different versions or isotopes of the element. So the only thing they have to have in common is the proton number, the atomic number, but their neutrons and therefore their mass are different. Average atomic mass is something you find on the periodic table. It's a decimal. This average is an average of all the different types of isotopes of mercury. So there really is no mercury, one type of mercury that has this mass. This is kind of like your weighted grade in campus. Maybe you're getting a 94.55%, but yet you've never scored that exact value on a test. So this is a calculated number. And again, like I said, it's calculating it based on the mass of the isotopes of that element. And it's not a normal average. It's not just add and divide by the total. It's a weighted average. So let's keep going. Mass number, this is the number I think we're really more interested in, especially as we get into nuclear chemistry. This is the actual mass of a particular isotope. And this is not on the periodic table. It's always a whole number, and it is measured in AMUs, atomic mass units. So it does have that in common with the average atomic mass, but again, like I said, you're not going to find this on the periodic table. It is not a calculated, at least it's a simple calculation, just protons and neutrons, but the average atomic mass is really a weighted average of the mass numbers of all the isotopes. So just a visual for you, it's really the mass of the atom is in the nucleus, so we ignore the electron mass because their mass is about 1/2000th of a proton or a neutron. So there's different ways when we're talking about different types of isotopes to talk about them. One way is to have the element symbol and then two numbers. One is a super, one is a subscript. The top number is going to be the mass number, which is the protons and neutrons. The bottom number is the atomic number, which is the protons. So we'll just do a few of those examples together. You can sure feel free to try these on your own and then, pause and then check, whatever you want to do. So here's an example, copper, and the mass number is 63, the atomic number is 29. So notice that the atomic number is here. This number, sometimes it'll match in a way, like if I were to round that, well, that would go to 64, but I'm not going to use that number. So this is the mass number. Remember, that's the weighted average of all the different types of copper. How many protons would it have? 29. And then the neutron number is going to equal the difference between 63 minus 29. So I like it when they're written this way because then you can just subtract to get the neutrons. So there's 34 neutrons. And then the electrons, for now, we're going to assume that we're electrically neutral. And we know electrons are negative, protons are positive. So if we have 29 protons, we would have 29 electrons. Another way that we can write isotopes to kind of be able to communicate to each other which one are we talking about. This one's easier like in text, or like if you were reading a newspaper article about uranium-235. It's easier to just say uranium-235 than to write the 235 over 92 in the U. So this way you give the element name and then you follow it by the mass number. So it doesn't give you as much information as the other way, but it's sometimes easier to be able to talk this way with someone. So nickel 59, if you wanted to, then you could look on the periodic table, find nickel, and the atomic number is 28. If you want to translate it, I like to sometimes, just because I'm trying to calculate neutrons. So the neutrons, there would be 31 neutrons. Electrons and protons are equal to the atomic number, which is 28. Here's another example. Again, mass numbers right here. I can look up the element on the periodic table. There's my atomic number, which is my protons and my electrons. And then I can just subtract to get my neutrons. And this one has 112 neutrons, so a lot of neutrons. And let's do another one. This one now, and this is kind of, I think, what you learned in 9th grade, was to take that and round it to the nearest whole number. That would be the most common isotope of tungsten. Don't plan on doing that unless I say that in the question. So if I were to write the hyphenated notation, I would write tungsten dash 184. So mass number is 184, atomic is 74, which is my protons and electrons. Neutrons will be the difference between these, and that ends up being, sorry, I have to look because I can't do the math really quick, 110. So a lot of times when I do this lecture in class, people ask, well, what about all those elements that don't, they have like a, it's hard to tell on this slide, let me get a bigger one. The average atomic mass is in parentheses. If you're wondering about that, it's because there are no isotopes that are actually stable. And stable, we're going to talk more about that when we start to talk about nuclear chemistry and radioactivity. So there is no stable isotopes, so they don't have one that they can then, you know, calculate how much % of that in nature and be able to do this calculated weighted average. It's not possible. The worksheet that you're going to do that goes with this lesson is pretty simple. I just want to point out a couple things. Remember that your mass number and your neutron number, you're not going to use the periodic table. You're going to use the one I give you. So for this problem, 85 protons, I would look on my periodic table, find the atomic number of 85 is going to be astatine. And we want to do hyphen notation here. So I'm going to put the mass number after. And then I can calculate the neutrons by taking 210 minus 85. And that gets me 125. And then remember, we're just going to deal with neutral atoms. So my electrons and my protons are going to be equal. And then one last slide, if I can get it to come up. So this is the second type of question on the worksheet, and I'm going to do the second one down here. So proton number is given, so that tells me the atomic number is 30, so I know it's zinc. I'm going to do the symbol there. Here I'm going to write out the name. The electrons are going to equal protons, and then I can sum these together to get the mass number, which is 67. Mass number, atomic number, mass number. So I hope that helps you guys.